Good morning. So we are today here on September 19. We are going to start the next module on probability and statistics. I plan to go over this module for the next 3 lectures, including today, there is 4 lectures. And on October 3rd, we plan to have a quiz on this topic, which is 2 weeks from today. Okay. If I figure that I need more time, especially I want to do one programming exercise with you all in class, that the one I mentioned about making an election prediction. If that takes more time, I might push the quiz to October 8th and then the exam to October 10th. October 10th, the Friday, that is October 11th and 12th. 12th is when your fall break starts. So it might work out well if I start a topic after the fall break instead of starting it before and then have like a 3 days gap. So it might work out that way. But as of now, let's stick to the schedule. Okay. I plan to be grading your homework as well as your past 2 quizzes in the next few days. Hopefully next week I'll post the scores on Canvas, okay, which you can view. All right. Any questions so far in the course before we start on a new topic? So for this particular topic, we are going to be using MATLAB. So I hope you have your laptops with MATLAB installed. Okay, we're going to need it. I'll also need some specific apps in MATLAB that I want you to use. It's called distribution fitter. If not today, by next lecture, I want you to install that add-on. I'll email it to you with the word distribution fitter. It's one of the apps that you can find on MATLAB, which we will need to use. Okay. All right. So coming to probability and statistics, it's one of those topics in which you either know everything or know nothing. In the sense that it sounds very intuitive, but if you try to push your understanding a little bit, it can be unsettling. Okay. So I want to ask, or I want to start by asking, what do you know about the word probability, chance, odds? That is one question. And then the other question is, what do you know about the word statistics? What is your understanding to begin? Probability, odds, chance. What do you know about those words? What does the word probability mean? Or chance? Or odds? Tell me, whatever you know or whatever you think. Likelihood. Likelihood. That's also a synonym for what we are trying to say. Likelihood. So what does it actually mean? Use some words without using these words. Percentage of certain event happening versus it not happening. Okay, so if you did a event, or if you define something as an event or did an experiment, if you have a certain outcome, and then versus the total number of trials. This ratio is fundamentally defined as chance or probability, right? You're all young people. I hope like more than 18. Have you been to Vegas? Have you done some gambling? Can you share your gambling experiences? Anything interesting mathematically? You want to say something?
I had $200 and then I had $0.
Okay, that is a summary, but yeah, go on.
The first and only time I gambled, my girlfriend's dad put $20 in the slots.
Okay.
Came back with the winnings from that, put it in one. So I put $20 in and lost it all.
Okay,
So,
so
yeah.
you didn't make anything out of it. So have you all played blackjack? Okay. No? Okay, maybe you can look it up, or there are a lot of movies based on the theme. I think Hangover is one, but I won't recommend anything. Okay, if you played blackjack, can you tell me one of the pivotal moments in the gameplay where you are counting on chance to help you?
Well,
You get an ace, you're waiting for the face card in the room.
So you need to make 21 exactly, right? So suppose you are stuck at like say let's say an ace. You need what is the next card that you need if you have an ace?
10.
10. You need a 10. There are so many cards that the deck has, but you are counting on one card or the number 10, which can come in four categories, like the yeah. So there are four ways you can get 10 out of say 52 cards. So that 4 is your favored event, and the remaining 48 are things that you don't care about. So the odds are, what is your odds of getting that favored card? That would be 4 out of 52. And it's not even 4 out of 52 because your fellow players also have some cards in their hands. So that 52 is not this what in the deck. It might be a lower number, but just for argument's sake, the odds are 1 over 13. There's a 1 in 13 chance that you will get that card that you are looking for or hoping for. All right, let's move on to some other topic. We all read the weather report, right? How do you interpret weather reports? When they say today there's a 50% chance of rain for Shelby County, what is your interpretation of that? Just tell me what you think. You don't have to be right, or you don't have to say what is supposed to be the correct thing. So say you are sitting here in Memphis, but Shelby County is a huge area. When they say 50% for the whole of Shelby County, are they telling you personally, Wyatt, if you sit here in campus, it could rain or not with 50% chance? Or are they giving the same prediction to me, I'm in Collierville, or it could be some other person, Bartlett, whatever. So how do you interpret these things? That is the question. What does this 50% actually mean? Yeah.
50% of the area.
50% of the area. What were you going to say?
Same thing.
So they are trying to say 50% of the area for which the prediction is made is expected to have rain, which would still mean that you could get rain in Memphis, I may not get rain in College. That's still possible. So which 50%? Is it the eastern half? Is it the western half? We have no idea. It's still random, but it says overall 50%. Okay. I want you to give me an example where else you encounter chance or probability. Another example, weather we have covered, gambling we have covered, what else? Where else do we encounter chance?
Tests, multiple choice.
Well, that isn't supposed to be a chance
I know.
thing. But let's not take that as an example. Where else do you encounter chance? Be specific, don't say everything. Don't talk like a politician.
Leaving your house, there's multiple.
So when I listen to these political speeches, like one politician goes, we'll provide this, we'll make it easy to live. Well, isn't that what you're supposed to do? Tell me how you will do this. Okay, go on. That's again like gambling.
Counting like red lights, green lights.
Okay, move on, interesting. Go on.
There's this one light, like I'd say like 1 out of 10 times, it's green for me, but the other 9 out of 10, it's always red.
So you're saying that each time you encounter a stoplight, a traffic signal, there's a chance you will be caught. There's a chance that you just made it, it was green all through, or this is Memphis, it became red and you still thought it's yellow and still kept driving. Okay? So if I start from home, it usually takes me 30 minutes. But on a lucky day when I don't get caught anywhere, I can make it in 25. On an unlucky day, it could be like 40. So what exactly is going on here? Let's spend a few minutes. Let's assume like a path. Let's say we start from destination A to destination B. And if you are if this is a 40 mph zone, okay, and suppose we are doing 40 and this is 5 miles. If you didn't stop 40 mph average, 5 miles, how long will that take you? 5 over 40 times 60. What is 60 divided by 8? 7.5 minutes. It'll take us 7.5 minutes to do 5 miles at 40 miles per hour. But suppose there are 2 traffic lights. Okay? And now, can you describe what goes on to make your transit time, which could be 7.5 minutes if you had no interruption, or it could be as long as say each traffic light lasts for say 90 seconds. It's pretty long, but we'll say 60 seconds. 60 seconds. So if you get caught in it, it adds 60 seconds to your transit. You don't get caught. So there are like, for simplicity, there are 3 possible outcomes. Do you see that? Either you don't get caught, 7.5 minutes. You get caught in either of the 2 lights, 8.5 minutes. If you get caught at both lights, 9.5 minutes. And just to throw in some variety, we can say here's a train line, which if you get caught, it's a solid 5 minutes to your transit. So if you compound this to 3 random events happening, light 1, light 2, and the train, your transit time now does not have a single value. Previously, when you had none of these, like 1, 2, and 3 are not there, your transit time is a nice and simple value, 7.5 minutes. You with me on that? Now, you have a range of possibilities. There is 7.5 minutes. So if you had 2 lights only, you have 7.5 minutes, 8.5 minutes if you got caught in 1 light, and then 9.5 minutes if you got caught in both lights. You're with me? And then if you then throw in the train line, can you list me the cases? It would be the ideal, the best case scenario. It would be 1 more light. It would be 1 more, 2 lights. You got caught in 2 lights, but not the train line. Then you could have, you got caught in 1 light and the train line. That would add 6 minutes to your journey, which would make this 13.5 minutes. This will be 1 light plus train. It can be either of the lights, 1 or 2, doesn't matter. They both add the same amount of time, right? In our scenario. And then you get caught in both the lights, which would be 9.5 plus 5 or 14.5 minutes. You're seeing a range of possibilities now. And just to make it a little more interesting, suppose the second light is not 60 seconds, it adds 90 seconds to your journey. Then the number of cases again will change because you have what is the possible list of your cases? No stoppage. That's your best case scenario. You got caught in light 1, but not the other 2. So I'll say light 1, but not the light 2 or the train. And then you got caught in light 1 and light 2, but not the train. You got caught in not light 1, but light 2, but not the train. Light 1, no. Light 2 and the train. And then you can also have the worst luck, L1, L2 and the train. Right? So here it's 7.5 minutes. Here it's 8.5. Here it's 10. Here it's 9. Here it's 9 plus 90. Sorry, 7.5 plus 1.5 is 9. 9 plus 5, 14. So here it's 14 plus 1, 15 minutes. So your transit time could vary from 7.5 to 15 minutes in this very simple example. You're with me so far? 75. Wow. Can't stand for 75. I have to walk and talk. To be sweating. Okay, so you see these range of outcomes, right? What name shall we give these possibilities? Louder, do you say this? So these are all events, and each event is possible. And the fact that there are several events possible leads to what we can call as a distribution of outcomes. That is, any experiment that you can define will usually have a range of outcomes unless it's a very simple experiment. Can you give me some examples of simple experiments which have very limited number of possibilities? Coin flip. There are only two sides, head and tail, right? So it has only two possible outcomes. So the distribution there, so if we say coin flip, the distribution consists of two outcomes, exactly two outcomes, head or tail. Can you give me another example of a distribution with very limited number of outcomes? Rolling a dice. A dice has like 6 faces, so it has to be either 1, 2, 3, 4, 5, or 6. Can you think of any other situation or event which still has a distribution which is very finite or has very few possibilities? One more example. Third will be hard because you already exhausted the two easy ones. Come on, think. You can fit most of life's situations into the coin flip situation. It's a boy or a girl. It's a donkey or an elephant. Right? I mean, at least here in this country. What other distributions can you think of? What other, okay, forget even these type of limited scenario situations. Can you think of some experiments? Yes.
Think like age range at a school.
Say it again.
The age range at a school.
Age range in a school. Actually, yeah, sure. That's a good example. So if we think of age range, even we might not even have to take like a school. We can say, well, let's take fourth graders, and based on their date of birth, just think about their age range. Most of them are first graders. Most of them are expected to be 6 years old. Some of them might be nearly 7. Some of them might be only just above 6. So you will have a spread there, depending on how many students you have in your class. You can think of such possibilities, or you can think of such experiments in which you collect data, and that data can be in any form. It can be a measurement you do in the lab. It can be a survey that you take. It can be a coin flip. It can be a dice. It can be, data can come in many flavors. Okay. Suppose you are in the lab, in your fluids lab or in the thermal lab, and you are taking a temperature measurement. You have a thermocouple. How many of you have seen a thermocouple or used one? So when you hook up a thermocouple to a readout, what do you see? You see a number, right? It says 25.2 degrees Celsius, something like that. What exactly is going on there? How exactly does a thermocouple work? Or in general, how exactly does any sensor work? Do you know? Okay, let me clarify. What I'm trying to think of is not the physical principle that is used to detect temperature, but rather a thermocouple in its construction is two pieces of wire that are joined together at a point. Do you agree with, are you aware of this fact? So a thermocouple is just two disjoint materials that are brought together. And when you expose it to a temperature difference, it creates a potential difference. That is the working principle of that sensor. All right, you create a voltage difference. Now, if you measure that voltage difference, you know that from a calibration chart, you can look up what the real temperature is. Are you with me in the story so far? Measure a voltage, use a calibration equation to convert voltage to temperature. This is what your handheld device does. That equation is already programmed in the device. You just need to hook up the voltage, it will tell you the temperature. Between that act of hooking it up to a readout and sticking your thermocouple in an oven or a bath of ice or whatever, that voltage, acquiring that voltage is the act of measurement. When you say you are measuring temperature, that's a misnomer. What you are really measuring is voltage, and what you are doing is inferring temperature. Are you with me in the story so far? You're not lost already? You're okay? You have a good poker face. Sometimes I'm like, am I saying the right thing? It's like stone cold. Like. Anyway, okay. So the act of measurement is getting that voltage read out. If you have that, you have the temperature. Let's think about how exactly this voltage is actually behaving. Okay, because it again comes back to statistics. I'm not randomly bringing up this example. So here's your, like if you have nichrome, nickel, chromium, okay, you have your thermocouple tip, your whatever you're trying to measure, that temperature is exposed here, and this tip attains the same temperature, and as a result produces a voltage difference that you need to read out. So you need to hook up a voltmeter. If you connect a voltmeter, it's going to read out a certain millivolts or something. Let's say for simplicity, it reads something of the order of 1 millivolt. Okay. If you paid attention to the voltage measurement, it will not be exactly 1 millivolt. It would be a range of values which might actually spread from 0.985. It could be a random sequence of numbers, 0.991, 0.912, 1.013, 1.101. It could be a range of values. And what your measurement device does is acquire like 1,000 voltage values in 1 second. So if you have a analog to digital converter, A to D converter, what it does is it acquires voltage samples at a set sampling rate. Like for example, 1000 hertz. 1000 hertz meaning within 1 second, my A to D converter is acquiring 1000 values of such voltages. Okay, this is what all your fancy biomet devices do. They turn electrical pulses into actual quantities. So this must be something you should be able to relate. So you acquire 1000 samples. What I'm asking you to think about is this is just not like a column of numbers, but it has, let's say, I acquired the sample for 1 second. I have a sequence of 1000 values of voltage. Okay, this is almost like doing 1000 voltage measurements to generate 1000 possible values of that voltage that you're trying to measure. Question is, among this big list, what is the actual true voltage that you should take and use it to infer your temperature? What would you do? The average? Yeah. So why do you think average is useful? Like what does average itself represent? You know what is average? You write x is x1 plus x2 and so on plus x thousand divided by 1000. And if you would allow me, I would replace this 1000 with n to denote that 1000 is just an arbitrary choice. It could have been 4000 or 5 or whatever. So the average, you use the average to represent all these numbers, right? Right? Good. So now let's start our discussion or let's put some fundamentals in. Let's not get directly to the average. Let's pay attention to these 1000 numbers. Okay? These 1000 numbers, if you actually look at them, they are not all the same. First observation. They are not all the same, and they are sometimes like in the 0.9 range, sometimes in the 1.0 range, and so on. You could do what is called as sorting. Can you? So before statistics, I'm sure binning, the word binning, binning, binning. Where do you encounter binning? What does binning literally mean if you just look at it as an English word? Separating and putting stuff into respective containers, which we call bins. What were you going to say? Putting into bins. So you do this at home, right? Your mom or your partners may be telling you clean up your room and put your laundry in its bin, put the dishes away, and like sorting things, right? That act is called binning. When we come to data, what does binning imply? What would you do with the data with regards to sorting the data? Group similar values together. The way I've written them, there is no particular sequence. And when I'm acquiring 1000 voltage values, I know the temperature is slightly fluctuating because the room air temperature is never like a single constant value. It's slightly fluctuating, so the voltage is slightly fluctuating. There is electrical noise. You get a random sequence of 1000 numbers which are not sorted, which are in some arbitrary order. The act of binning is to say, among this list, let's say my lowest value is like 0.900 millivolts and highest value is like 1.100 millivolts. Let's say I have a range, okay? And I take this range between 0.900 and 1.100. That's like a spread of 200 units between 1100 to 900, right? And I'm going to chop this interval into 10 equally spaced or equal width bins, meaning I'm going to take a width of 20 units. So the next bin would be 1080, 1060, 0.920, 0.940, and somewhere in the middle will be 1.000. Now bring back that idea of binning. What is binning? You take the first object, it is 985, you know it has to fall. Just for space sake, I'm going to say my bin width is going to be 50 units. 950, 100, 1050, and then 1.10. Pardon my drawing skills, they are terrible. Okay. So I look at the first object, it is 985. Where should I place it? It's between 950 and 1000, right? So I should register a count plus 1. It's actually a counting process. I took 1000 samples. I can take 991, and turns out it would also be here. 912 would be here. 1013 would be here. 1.101 will, for simplicity, will make this 1.099 would be here. I'll take 1,000 objects and I'll put them in respective bins. At the end of this exercise, I'll have something that represents how many objects are found in each bin. I had 1,000, right? Let's say around 500, 502 are here. Around 300 are here. I'm already at 800, so maybe I should draw this down. So say this is about 150, and whatever is remaining, which would be 800, this will be 50. So this process of sorting the objects into respective categories is called binning. If you ask me, the definition I would say is the process of sorting the objects or counts or values or readings. These are all synonyms essentially. Readings into respective bins. This is binning. I'll give you some time to write up to this because some of this I write it in a very quick way, but it's important stuff. I want you to write this stuff and record or write down as much as possible about this exam. It's getting recorded, so you can also watch it later. Okay, so just some definitions. We have raw data, sequence of data in the form of either numbers in the case of measurements, it could be choices in the case of survey, there are many other forms. Most of them are either like numbers that you can represent. It could be like 1.005 numbers like those, or it could be choice. It could be that it could be a political poll. It will say candidate A, candidate B, candidate C, and so on. So usually it is just a sequence of data. So suppose you did one experiment. The experiment is to flip a coin 10 times. How will your data look like? So you did 10 coin flips. It has to be a sequence of head or tail 10 times. So it could be like a head, head, tail, tail, head. So it's 10 numbers. Okay, you can do this. Okay. So in our example, measurement example, a list of n equals 1,000 voltage values. This is what we call raw data because we have not done any kind of operations or processing on that. Okay. Then you have the act of binning. Binning is sorting the raw data and representing them efficiently. What do I mean by efficiently? Take the coin flip example. You did 10 flips. You have a sequence of head and tail. How will you convey it with fewer numbers or in a more compact form?
0.
Louder, please. Well, you don't know it's half. I could be some lucky dude who got 9 heads and like one tail. You can just say the number of head outcomes and number of tail outcomes. Instead of using 10 numbers, I am here using only 2 numbers. So it becomes more efficient, right? When you look at the measurement example, obviously you don't want to be walking around with a sequence of 1,000 numbers each time. So how do you represent this more efficiently? Yeah.
Like you do in your graph.
So we for this situation, for the coin flip situation, I can write head, tail. I can draw a bar graph saying this is 9, and for tail this is 1. This is a distribution, but it has only 2 possible values, so it looks much simpler. Okay. Whereas for the 1,000 values, the binning process results in a histogram. So binning of large data sets consisting of numbers results in a histogram. Okay, so this is a histogram. Histogram. I believe the word hist means counting in some language, Greek or something, which I, as an engineer, don't care about. But histogram, I care about. All right, let's look at the anatomy of this histogram. There are certain aspects here. Each bin has a width. So there are bins. There are the width of the bins or bin width. Okay. And what is on the y-axis? What does the height of the bin represent? Frequency or count, right? Frequency. Why do we say frequency? Why did you use the word frequency? How frequent the value falls between 0.9 and 0.95, that is represented by this 50. That is why we call it a frequency. Okay, it's literally a count of how many times it happens. Okay, so the histogram is defined by the bins and their width and the frequency or count in each bin. Okay, what is the difference between the raw data and the histogram in terms of information? Which has more information?
All data.
Raw data has more information because there is no rounding off, there is no averaging. So think about this. Everything that was between 0.9 and 0.95 is now lumped into a bin and it says 50 of those. You lose information when you do binning. You can't recover the 0.912 anymore. It's just represented by this bin, which is the basics of your grading system, which you know for so long now. You get an A, even if you got 95.1 or 99.9, you are an A. Why do you think people came up with such a grading scale instead of a point scale like they do in England, India, and many countries where they still go with points instead of letter grades? It's not that much trouble. We just have to, in the transcript, you print 95.1 instead of calling it a A. What's the big deal? Why do people care to do this at all? I will tell you that those countries also are now adopting the letter grade system or have been adopting it for the last several decades. So it's slowly going away. But if you went back 100 years or even the time I was studying in India, we didn't know grades. We had only scores. What is the logic behind grades? So you get 96. You get 94. You are an A minus and you are A. Why this kind of, in just 2 points on this side and that side, you are getting one letter grade difference. What is the principle in it?
Get better on it.
So the general idea behind grades is when we give an exam or when you go through a course and you get a score, the score you get, if you did exactly the same course again next time, like another trial of the same experiment, you will get a slightly different score because you are not. It's like a multiverse thing where you went through this course once. If you went through the same course again, there will be something you do differently. So it is impossible to say that a student who gets exactly 97 is good, but someone who gets 95 is not good. It's impossible to say it that way. Just because you got 94 doesn't make you any less in terms of understanding. If you're 94 and say 94.5, like there is not much to take between those two scores. That is why we came up with the idea of lumping closely related scores to say either you got a 91 to 95. In generally, you are the same ballpark, so we'll call that one letter grade, and then the next letter grade. And so, of course, I keep using the 90s, hoping that you all will kick ass and be getting 90s. I could be talking about B's and C's that I don't want to make you feel bad. All right. So you have the histogram which has less information, but what is the advantage of using a histogram?
More concise.
More concise, and you can represent your entire data with very few numbers. This is not a big deal when you're dealing with, say, 10 numbers or 100 numbers or 1,000 numbers. But when you have to deal with terabytes and terabytes of long lists of numbers, you want a compact representation. That is what histograms are. Okay. So how do you summarize the histogram? Or how do you, okay, maybe not, that's not the right question. What I would say is, so I have on one side, I will write raw data, which is a sequence of numbers that I'm going to write as x1, x2, and so on, xn, where n is usually a large number. Okay. On the other side, I will call this root or bin data, okay, which is not represented by a sequence. It's represented as, we call this, maybe I should use a, be careful with my nomenclature. So I'm going to say, so what I'm trying to say is, if I say x1, y1, y2, or uppercase x1, x2, x3, xn. So if I say x1 to x2, and then x2 to x3, and so on, xn minus 1 to xn. This is my bins. Could be like 900 to 950, 950 to 1000, 1050 to 1100, and so on. So this is the bin starting point and ending point. Okay. And for each bin, we have a count or a frequency. So it should be 50, 150, 500, 300, something. So I'll call that F1, F2, and so on, Fm. So I'll say bin number 1, 2, M bins. Here we had like 4 bins, M equals 4. In general, let's say M bins. So you can see that to completely specify this histogram, you need M values. frequency for each bin. Okay, you also need the start and end for each bin. But if your bins are all equally spaced, like their width is constant, you just need to know the start and the bin width. So you need to know the start and the bin width. So m values and then two more values. So m plus 2 completely summarizes the data. Right? M plus 2 completely summarizes the data. On the raw data side, you have all the data if you are handling it directly. And if n is like 100,000, this is a huge data set to handle. Whereas this bin or group data, if m is say, for example, m is 20, this is still not bad. 20 plus 2, 22 numbers to handle. Here with me so far? Okay. Mary, very good. Okay. All right. Now let's come to the calculations that you know of. How do you compute average? For raw data, what is average? You tell me, you know this. Sum of the numbers, I'll say x1 plus x2 plus and so on, xn divided by n. You know this. Same quantity for the big group data. How would you compute average? So look at this histogram. Actually, a more simpler example would be if we took all our heights, like each of us, we have a height, right? If I ask you what is the average height of the people in this class right now, it's pretty simple. You would go around asking each person's height and get the average that way. If you turn that height into a histogram, let's say we have people from 5'6" to 6'5", 6'2", that range. You would count how many people are in each range and put them here to get the histogram. Either you do histogram or the raw data, you can still compute the average. Okay. I'm now asking you, how would you compute the average if you have group data?
Take the middle number in the bin, multiply it by the frequency, do that for all the bins, divide it by 1,000.
So the whole idea of winning kind of lump them together, right? 912 and 948 are now counted as the same. To make up for that, we'll take the midpoint, which is like 925. So we can say I have this bin start and bin end, right? So I'll take the bin midpoint, which is x1 plus x2 divided by 2, and that happens f1 times. That is, in other words, the value x1 plus x2 divided by 2 occurs f1 times, nominally speaking. Okay, so I can say f1 multiplied by x1 plus x2 by 2 plus I can also write f2 occurs x2 plus x3 over 2 and so on. I'll go up to fm, which occurs not n, it's m, xm minus 1 plus xm divided by 2. This is count, right? Count multiplied by midpoint. Count multiplied by midpoint. This is sum of all the values divided by the total number of values. So we still have to divide this by F1 plus F2 plus F3 and so on, Fn. So this will be the average if you compute it using a histogram. This making intuitive sense to you, right? So this is the average, okay? What about standard deviation? Have you heard of this term? What is standard deviation? If you haven't heard, you take this X. Okay, tell me what average means in the first place. You have your possible X values. That is your, if you actually represent these 1,000 numbers on a line, they are going to be spread out. Average is literally their midpoint. It takes the distances and literally draws a line that is in the center based on the distances. Okay. Standard deviation is, if this is your average, it's like asking, let's say the average height of this room is 5 feet 9 inches. I happen to be 5 feet 10 inches. My deviation from the average is 1 unit or 1 inch, right? So this is X bar. If I calculate X bar minus X2, that is the deviation of X2 from the mean. And by averaging all such deviations, we get what is called as standard deviation. So we write standard deviation to be sigma x equal to x1 minus x bar. The fun fact is this x1 or this x1 could be lesser or more than the average. To account for that, we square it and then we write x2 minus x bar plus and so on, xn minus x bar squared, the whole thing divided by n minus 1 square. You know, you may ask why I'm putting n minus 1. I'll get to that story in the next lecture. There is a reason for this n minus 1. There is a reason why this is n, and then there is a reason why this is n minus 1. Okay, we'll get to it. So this is standard deviation. How do you get standard deviation from your histogram? Think along these lines and tell me. I'll help you by writing bin number 1, 2, m, and then bin midpoint. I'll give it a new symbol. I'll call it x naught x1 center. This is equal to x1 plus x2 over 2, x2 center, xm center. So this average can be compactly written as x bar equals f1 times x center 1 plus f2 times x center 2 plus and so on fm x center n divided by f1 plus f2 plus fm. This is average. Look at this and try to think, how will you get standard deviation from here?
The xc1 minus x bar squared plus xc2 minus x bar squared.
So you're trying to weightage You're trying to weightage a quantity, which is the value multiplied by how many times it appeared. So if I break this down, this is frequency multiplied by value being considered divided by frequency total. That's what the denominator is. So when I say average, it's like asking how many times that did this bin occur, how many times did this bin occur, and so on, divided by the total number of values. When I'm saying deviation, I can say if x bar is my average minus xc1 is the deviation of the midpoint of bin 1 from the average. It's the deviation of the midpoint of bin 1 from the average. And as we talked, this xc1 could be the left or to the right of the midpoint of the average, which is why we take this value and write x bar minus xc1 and square it. Plus f2 times x bar minus xc2 squared and so on. You're writing up to here, I'll wait for a second and then I need to erase this. You're okay. Can I erase this? Santiago? Plus fm times x bar minus xcm squared divided by f1 plus f2 plus and so on fm minus 1. I told you I'll tell you the story of minus 1 later. So for now, take my word. Okay. So this I have to take a square root. Okay. So whether you are handling the raw data or you are handling group data, you can get the same quantities calculated. Okay. And what is the use or need for grouping? We don't want to walk around with 100,000 numbers. We want to compactly represent them, which is why we do binning. Okay. And when you do the binning, you get what is called as the histogram. So that, remember this skyline. Okay. It's basically a stack of skyscrapers. You remember this imagery in your head. A histogram essentially tells you how that quantity is literally distributed. That is, which numbers occur the most, which numbers occur less frequently. That's what a distribution is supposed to tell you. Okay, so I'll write it here. A histogram shows, I would say graphically or visually, how the quantity, how the values, which could be values of height or values of voltage or values of temperature, whatever quantity you are dealing with, how the values are distributed. That's what a histogram shows. Okay. It's a lot of theory today, but next lecture we will definitely do a lot of problems. Okay. So bear with. Okay. Drop your pencils. Now let's talk a little bit. It shows you how it is distributed, right? You can obviously see that there is some common features in the way quantities are distributed. Like for example, if you do the coin flip experiment, whether you do it or I do it or you do it, there are always only two outcomes. So that skyscraper is going to look like, let's say this is head, this is tail. If you did 100 coin flips, or if you did any large number of coin flips, you kind of know that you are going to get 50 of these, or 50% of these, and 50% of these. A given, right? So there is only one way that this can be distributed, or I shouldn't say one way, I should say there is a specific way that this is distributed, which is there are only two outcomes, either this or that. And when we say coin, we always assume it's a fair coin. And in textbooks or in like they say a fair coin. What is a fair coin? Do you know? How do they cheat with coins? Do you know that?
We have to wait.
Add more weight to one side to make one side fall up more often. So make the head heavier so that the tail falls up more often. So you could have, in that case, instead of a fair coin, a doctored coin. Something in which the probability of getting a tail is not 50%, but let's say it is 70%, and the probability of head is remaining 30%. Okay, even if it is a fair coin or an unfair coin or whatever coin, there are only two outcomes. And these type of distributions where there are only two outcomes are described by what is called as a binomial distribution. I am though skipping one step. I'm suddenly start using the word distribution. The previous connection I made was to say the histogram shows you how the values are distributed. And now I'm using distribution as a noun. So what is the missing connection? What is a distribution? From this sentence and from this example, can you define or can you try to say what a distribution means? It is a pattern or a function that represents the spread of data. It's a thing. When I say the word, when I say the sentence, this is how the values are distributed. Distributed is an adjective, whereas distribution is a noun, meaning it's a name of something, right? That something happens to be a function that describes how the data is distributed. So distributed plus function becomes distribution. Okay, so when I look at this sort of data that looks like a skyscraper with a rise and fall, what's the distribution that famously comes to your head?
Okay.
Bell curve, Gaussian distribution, normal distribution. These are all names for the bell curve. Okay, what exactly is the bell curve? Can you just tell me what you understand?
Should show the average and then your outliers like on a.
So let's say we have a class of 100 students, hypothetically speaking. I have the grade distribution, A, B, C, C plus, B plus, A minus, and so on. And I'm telling you the grades fell perfectly on a bell curve. What's your understanding in this?
That they all grouped around a certain value. Didn't have to be in the middle, could have been at 30% still. Or
Qualitatively, you are correct. Like by qualitatively, I mean intuitively, we all have an understanding of what is bell curve. When we all say, when I have class and when I'm starting from home, I know my transit time to the university is like 30 minutes and I have like 45 minutes exactly remaining. I know that I'll hit it mostly in 40 minutes and me taking 50 minutes to get to the university is like a rare event, so I'll chance it. Most of the time it's 30 minutes, right? So I'll take the chance. So we all intuitively kind of get it in our heads, in our actions and so on. But can you be more formal and exactly say what exactly is the normal or Gaussian distribution. Let me help. One second. So you have this, let's say this represents the grade distribution, okay? I have in my class, let's say I have in my class, most of the class, in a class of 100, let's say around 52 happen to be B. Okay, and then a fewer of them, let's say around 20 of them get B plus. And then even fewer of them, we are already at 72, let's say around 5 of them get A. And then on the other side, let's say I have B minus and then C. So a similar number, let's say 18 get B minus, so that is 60, 70, 90, 95, and then 5 more end up with C. That's 100 total. When I say this is distributed like a bell curve, or it is Gaussian distributed, what exactly am I referring to is following that so-called bell curve. Put something like this.
Values to the left and right of the middle.
It's not only those, it's also those. What we are referring to is, if I take the bell curve and feed in an average and a standard deviation, it will tell me exactly the proportions for each bin. That is, suppose you didn't know anything about distributions, okay? All you did was to take a list that I gave you, which had 100 C, B minus, B plus, and A. Like I gave you 100 entries of those. I didn't even tell you the names of the students. You made the histogram by counting how many C's, how many B's, and so on. That part you understand, right? It's literally counting. If I take this histogram, I told you you can completely specify the histogram by telling the frequencies and specify how to construct your bin spacing. A distribution goes one step further. It basically uses a function to represent this entire histogram in terms of its average and standard deviation. If I tell you two numbers, that is the average and standard deviation, plus a function like a literal formula, using that you can predict the rest of the distribution. That is what a distribution does. It is a mathematical representation of a variable or a random, like a possible values that can be completely specified using some measures of that population, like average and standard deviation. If I tell you that, let's say I tell you, you are my teaching assistant, I give you a list of 100 grades, I tell you my average grade is a B. Okay, and I want more than 1/6 to be in the A and no more than 1/6 of the bottom 1/6 to be in a C. If I tell you these three pieces of information, with that you can actually populate the rest of it, because that either you can see the original data or take the distribution function that I give you and the constraints which is equivalent to the original data. At the end of the semester, I do this. When I have a class of say 50 students, I tell them the grade distribution. I don't tell who got which grade. I'm not supposed to do that. I tell them the grade distribution and say the class average GPA is like 3.1 and the class average grade is B, with 52% of the class getting a B, 25% getting a B plus, and so on. Okay, so this is sort of a maybe a little long-winded explanation of what is distribution, but let me get back to this. So we are here. A histogram tells us how the data is distributed. Okay. At this point, although I gave you that example and everything, I want to make a distinction. What is the distinction? If you take the coin example, coin toss and voltage measurement, there is fundamentally something different between these two. What is that? You flip the coin 100 times, you get a sequence of head, tail, and so on. You acquire 1,000 voltage measurements, you get a list of numbers. What is different between that two distributions? Both are distributions, both are sequences, but what is different? Sure, you can do 1,000 coin tosses. Like you can match that. It's not the length of the data. Something else is different between them. What? So you are saying that this is a continuous numbers, meaning you could have values which are 1.000, 1.001. You could even have more decimal points and so on. Like these are numbers. Here there are on, so you can say that if I say I get 1,000 numbers, they are all continuous in nature. Okay. What about the coin toss? What are the possible outcomes? It's discrete. You can either be a head or tail. You can be a 0 or a 1. You can be a blue or a red. That's what we mean by discrete. So this is an example of a discrete probability distribution. And this is one example of what is a continuous probability distribution. Can we get one more example of something that is discrete, something countable? When I say discrete, I mean countable. You might ask me, is voltage not countable? No, voltage is a value that you can represent like a continuous real number, but real numbers are not countable. Why? If you write integers 1, 2, 3, and so on, you can count objects that correspond to these integers. But when I write 1.412, that is fractional. You can't count it. You can't have 1.412 objects. Yes.
Floors of cars, something. That kind of discrete?
Yeah.
Yeah.
So if you have 1 through 10, and then you have your the J, the Q, the K, and the A, that's 13 cards times 4 suites. So you get 52 cards. So any probability that you would do will be in multiples of 152. Right? So if I ask you the question, how many red cards are there, or what is the chance of drawing a red card, that is 26 over 52. Or if I ask you what is the chance of drawing a numbered card, what would your answer be? So 4 times 4 is 16, 52 minus 16 is 36. So 36 out of 52 is your chance for drawing a card with a number and not with a letter, not with a character. Okay, so we had coin toss, we had playing cards. What else? Countable random variables. When we did coin toss, we kind of exhausted all the binary choices in life. You can't come back and say boy or girl, Democrat or Republican. No, all that is done. What other discrete distribution can we think of? Sorry? Okay, dice. So the value that you get in a dice, that is sure. 1, 2, 3, 4, 5, and 6. And if you have two dice, the sum of the numbers or three dice and so on. So all the variants of dice, good. One more example. I want you to get to one important class of quantities. What else can you count?
What was that?
What else, what other quantities are random, but you can count it?
Like purchasing things like phones or something, like the chance that somebody will go with like Apple or Samsung, would that be discrete?
Yeah, it's still again binary. It still falls in our coin toss. If you say your two brands are Apple and Samsung,
Yeah,
it's head or tail. It's just a name that's different. Or if you say Apple, Samsung, and some other brand, it comes into the dice analogy. It's multiple but not binary. So that's not, we are already covered. What else?
It's like decimal,
Sorry?
like fractional or decimal.
No, I want to ask you for quantities which have a finite number of outcomes. Like, for example, if you think of, just think of how many car trips you make in your life. Okay? Or forget car. Plane is a better example. We all do plane trips, right? They say that with the engineering and everything we have now, the chance of a airplane accident or airplane crash is 1 in 1 million or something, 1 in 11 million or something. But people do get caught in crashes and lose lives and so on. So did they do 11 million trips to get caught in that? No, right? Obviously they didn't do that much. So when most of us do plane trips, nothing bad happens. So you can define that as an outcome 0. So in your entire lifetime, if you can count how many times there was a plane accident in which you were involved, most of the time the answer is 0. For an unlucky few, it might be 1. For an even more unlucky few, it's as rare as it sounds, it could be 2. If you are an Air Force pilot and you have seen a lot of battles, it could be more than 2. Right? So again, I'm talking about rare events like accidents, cancers. Like most people don't have cancer. Some do have a cancer. But there are some very unlucky people who happen to have more than one cancer in their lifetime. Right? The odds of those in the population is extremely small. That's why we use the term the odds are astronomical. Why do we use that word? Because space is such a big entity, most of it is empty. If you launch yourself in a space shuttle and go away, you might never meet another object at all. You might just fly into space and never meet an object for your entire life or for many light years combined. That's why the probability of rare events is called astronomical. Here's a question. How did it feel like when the last time there was an asteroid impact on Earth? Were you around? No, right? It's supposed to have happened many million years ago, wipe out the dinosaurs and stuff. But since we don't live long enough, in our lifetimes, we think everything made out of concrete is just golden. It'll just stay on forever. Because for us, forever is like 70 to 90 years, something like that. Okay? So the biggest class of discrete probability events are rare events. Let me give you one last example before I wrap this up. Have any of you lived in an earthquake-prone zone? Where?
California.
Where? California. Southern California or North?
Yeah, southern, like right on the 1000 is.
Okay, good. I spent 1 year there. Okay, so do you know what is the average time between major earthquakes in that Southern California region?
Major,
Major, not like daily quakes.
probably 30, 40 years.
30 years.
Yeah.
Okay. So they say that every 30 years there is a major earthquake. And how did they come up with this number? They have looked at seismological data for, let's say, last 200 to 250 years and counted as many events divided by 250 to come up with 1 in 30. Okay? Does that mean if you live there for 30 years, you will definitely see an earthquake? Why not?
It's just like the distribution of it. It's not. It could have happened, like, there could have been a major earthquake, it happened 5 years apart from each other. The next one didn't happen for like 70 years. Then it could have been like 3 and like 10 years, so.
So you are clearly seeing that this is a distribution, not like a repeated periodic event. It's not like every 30 years, like a clock, it's going to happen. Right? In fact, what my advisor back then told me is there hasn't been any major quake since 1988 or something. So they are due for one. And he was saying this in the 5th floor below the 5th basement floor. There is five floors below the ground. I was new to California and he was saying this, oh, we are due for an earthquake. Wait, 5 floors above me and you're saying we need an earthquake? Anyway, all right. So you see there's a distribution. Santiago, what do you want to say? Same thing. Okay. So if you live there, how long did you live there?
20 years.
22 years. So in 22 years, how many major quakes did you see?
Depends what, like major, like what's major?
Major
like-
means something that makes international news, something that's like, say, Richter 7 or
Like a
above.
7, 0, yeah.
None. You didn't see anything. But can you, would you be able to calculate what is the chance of seeing an earthquake in a zone where the average is 1 in 30? You live there for 22 years, I lived there for 1 year. If I am unlucky enough, I could have seen an earthquake in that 1 year, but how do we estimate these probabilities? That is what we are going to see in this module, okay? But along with binary events, so I'll start naming them. So I have binary events, and then I have finite sample space. Like this is your cards, your dice, okay? Anything that is finite, like 52 or 6 and so on. So this is your coin. And then you have rare events. Rare events, like accidents, earthquakes, and so on. Okay. These are all countable. That's what I want you to see. When I say binary events, you can ask what is the probability of getting 5 heads in 10 flips. Or you can ask the question, what is the chance of getting a number which is either 2 or 3 in a roll of a dice? What would that be? You have 1, 2, 3, 4, 5, 6. You are interested in these two. This you define as your favored outcome. So that is 2 out of 6 outcomes or 1/3. Okay. And rare events, it's like asking if something happens at an average of 1 in 30 years or something, what is the chance that we will experience 0 events, 1 event, more than 2 events, and so on. That we'll also see how to do that. So this is all just to kind of get you motivated, but then we are going to see the math behind this. Coming to continuous probability distributions, couple of examples, and we just have a minute, so I want to wrap up here. What are quantities that are continuous? We already have an example right here, voltage. What else? Height. Your height is, let's say, 5'8". It's not precisely 5'8". If you got a fine enough scale, it will keep on, changing. So it's a continuous number. What else?
Velocity.
Velocity, all physical quantities. Most physical quantities, velocity, temperature, pressure, everything is continuous. Anything else?
Position,
Sorry?
position, like geographical position.
Sure. Position is again, it comes under measurements. It's yeah.
Could you say like childbirth, how it fluctuates, but it's supposed to be continuous? like
You mean like the number of
per
child?
year? Yeah, could you say something like that?
It is actually every child is like a discrete entity, but when you deal with scale, that is when you deal with thousands or hundreds of thousands or millions, it becomes less important to worry about plus minus one fluctuations. You might as well treat it like a continuous variable. So good point. So what you are referring to is quasi continuous quantities that are not really continuous, but you can approximate them as continuous. Last example, if you take currency, like money, what is the lowest amount of money you can handle? The penny, 1 cent, right? So technically speaking, it is not a continuous variable. But when we handle millions and billions and trillions, it doesn't matter to worry about $1 level precision. So we treat even money like continuous variable in economic models. Okay. So hopefully this session kind of got you into thinking about quantities and random values. These last point for today, we are using the word probability distribution to denote the variation or the patterns of variation of quantities which are called random variables. That is, in our example, the voltage, the coin sequence, the rare event sequence, all those are random variables and they follow either a discrete pattern or a continuous pattern. Okay, we'll pick this up on Tuesday. Thank you.